Hello guys, we meet again for lecture 15. So this will be the last lecture for chapter 4. So in lecture 15, our topics will be on Laplace transform for passive devices, which include resistance, inductance and capacitance. And afterwards, we're going to use this knowledge to be applied in Laplace transform in circuit analysis. So let's start with the Laplace transform for resistor. Okay. Basically, lecture 15 will be actually an application as what I've stated in lecture 13 previously, in which Laplace transform is used to solve a circuit analysis problem. Okay, so before we can proceed with the circuit analysis problem, we have to understand how Laplace transform is being used for the basic passive devices in a circuit, which include the resistor, inductor, and capacitor. Okay, so for resistor, we know that from the Ohm's law, the relationship is V equals to IR in time domain. Yeah. So when we do a Laplace transform, so it will not change much in terms of the equation. The changes will only be on the time domain to the S domain. Okay, so we can have a VRS. Sorry. So we can have the VRS is equals to R of IRS. Okay. All right. So in this particular case, we know that the impedance of the resistor is R. Okay, so in terms of circuit diagram, we can have that if we have the resistance of R in time domain, so the voltage VR is the voltage across the resistor and IRT is the current that passes through the resistor. So when this circuit or when this component is said to be transformed into Laplace, we can have the VRT now becomes the VRS, which is the voltage across the resistor. R will maintain as it is, the resistor's value, and IRT now becomes the IRS. Okay, so this is a transformation of resistor in time domain to a resistor in the S domain or in Laplace domain. Yeah. Okay. So next we proceed with the Laplace transform for the inductor. So we know that the relationship between the voltage and the current of the inductor in time domain is given by VLT equals to L of DILT over the dt. Okay, so in order for us to transform into the S domain or Laplace domain, we have to adopt the properties of differentiation, this DILT over dt. And if you can recall back the properties of Laplace transform in lecture 14, okay, so we can have that the Laplace transform for this equation will now become the VLS. So L will be there. And this DILT over dt transformation for it will give us SIL of S minus IL of 0 negative. Okay, so this is based on the properties of differentiation. Okay, so why we have 0 negative here? So 0 negative basically is a voltage at the steady state condition. Yeah, steady state condition. Okay, which is the initial voltage value. Okay, so I think this one can be further explained when we solve some circuit analysis problem later on. Yeah. Okay, never mind. So for the time being, we accept that this IL0 negative is the initial voltage of the inductor at the steady state condition. Okay, so when we proceed with this multiplication, we're going to have the VLS will be equal to these terms here. Okay, so in this case, we know that the impedance of the inductor will be equals to S multiplied with the L, yeah, S multiplied with the L. Okay, let's have a look at the circuit. Yeah, so the components of the inductor in time domain will be equal to this. Yeah, so VLT is the voltage across the inductor, ILT is the current across the inductor. So when this component is said to be transformed into a Laplace domain by applying this equation here, okay, so we know that VLS here is the voltage across the inductor, yeah, from positive to negative. ILS is the current, yeah, a current which is propagating or flowing from the positive to negative point or terminal. Okay, so we know that from the equations here, SL is the impedance. Okay, so we have SL, the impedance, and then we are going to have Li zero negative, which is a additional voltage value. Yeah, additional voltage value, which can be represented as this voltage source. And because of negative sign here, the polarity of this voltage source is against the polarity of the current flowing in the inductor. Okay, right. So there's a big difference in terms of the transformation of the inductor in the time domain, and here is in the S domain. Okay, all right. Right, so this is another way of transforming the inductor. Previously we used a voltage, and then we have the current. Yeah, it means the current is written in terms of the voltage. But in this slide, we are writing the voltage in terms of the inductor. So this can be obtained from this equation. Yeah, from this equation, we are writing the current or the voltage in terms of the current. So please work out for that. We're going to have ILS should be equals to the VLS over SL, and the zero negative divided by S. So we're going to have this. So in terms of the circuit or transformation circuit, yeah, transformation circuit. This is in time domain. So in Laplace domain, we are going to have it to be looked like this. Okay, where we have the current, the ILS is the current. Okay, this is the current, which is returned to be divided into two paths. The first path is the current, yeah, the current which is originated or contributed by the voltage, sorry, not the voltage, the current flowing in the inductor, yeah, which is the VLS over the SL. Another one is the current source, yeah, which is obtained from these terms here, which is IL zero negative divided by S. Okay, so please work out for this. Hopefully you understand about these issues, yeah. Okay. All right. So why we have these two kinds of circuit transform for the inductor? So the reason why is that some problem can be solved by using a Kirchhoff voltage law, right? So and other problems can be solved using the Kirchhoff current law. Okay, so if you're using the Kirchhoff voltage law, by right you have to transform the inductor in terms of the voltage like this. But when you are solving the circuit problem using the Kirchhoff current law, yeah, Kirchhoff current law, so you have to adopt this method of Laplace transform for the inductor. Yeah. Okay. Hope you are clear about this Laplace transform for the inductor. Okay, so this is the next one, which is the Laplace transform for the capacitor. So knowing that the capacitor equation is given by ICT equals to C of dVct over a dt. So again, we can have when we transform this equation, yeah. So basically, the transformation of this equation will be similar to what we have seen in the previous slide. Okay, so I'm going to proceed with the next slide first. Yeah. Okay, so if we transform this equation in time domain, so basically you're going to have this in a S domain. Yeah. You're going to have IC of S equals to SC of VCS minus C VC of zero negative. Okay. So in this case, we know that the impedance of the capacitor shall be equals to 1 over SC. Yeah, 1 over SC is a Laplace transform for the capacitor. Right. So in terms of a circuit transform, so this is in time domain. So when you do a Laplace transform, you're going to have this, yeah, ICS, which is the current, shall be equals to 2 path The first one is the current contributed by the capacitor itself, and another path is provided by a current source. Okay, please note that since we have the current is negative, so the direction of the current source is against direction of the ICS. Yeah. Okay. So I proceed with the previous slide. Okay, this is the previous slide. Yeah. Which is obtained from these equations here. So we are now writing the ICS in terms of the BCS. Yeah, we are now writing the ICS in terms of BCS. So we're going to have this. We're going to have this term. So you can work out for this. Yeah, you can prove on your own the equations that relate the ICS and the BCS. Okay. So in terms of a circuit transform, we're going to have this is the component in time domain. In Laplace transform, we're going to have 1 over SC. Okay, this is the impedance of the capacitor. The VCS is the voltage drop across the capacitor. Okay, because the capacitor is a VCS. Okay, and ICS is the current flow from the positive to negative terminal. Okay, so note that this is a voltage source V0 negative over the S. Okay, so from here we are going to have this will be your voltage source. Yeah, so the voltage source will be having a same polarity with the polarity of the capacitor because of the positive sign for these capacitors. Yeah, okay. Hopefully you are clear about these circuit. Transformation circuit. Okay, and Laplace transform for the passive devices, which is for the resistor, for the inductor, and for the capacitor. Okay, so I can say that it is a must for you to memorize this equation. Okay, but actually this equation can be obtained from this specific equation in time domain. So you just need to do a Laplace transform to get these equations. Yeah. All right. So I'm going to stop here. So in the next part of lecture 15, you're going to see how those knowledge that we have learned in this part 1 will be used in solving the circuit analysis problem. Okay, so with that, thank you. I'm going to meet you in part 2 of this lecture 15.